All right, just before we get on with the examples, I want to remind you that in your data booklet, you have this diagram that shows you how to represent a male, a female, a mating or a mating between close relatives. It tells you that there should be Roman numerals to identify each generation, and there should be Arabic numbers, which are just regular looking numbers for each person in a generation. If you need to represent twins, you have two ways, identical or non-identical. The difference is if they're not identical, you don't put a line in between them. The thing that I think most people have questions about is when am I supposed to color one of the people on my family tree charts? All it says is that this individual is affected. That means has the trait that you are investigating. So you will decide which trait that is. For example, if in your family tree you were doing rolling the tongue, that one's pretty easy. If they can roll their tongue, you color their box in. If they can't, you don't. On some of the other ones, like is it your left thumb or your right thumb on top, there's not a natural choice to color in, so you pick. Just make sure in the title of your family tree it says, family tree for having left thumb on top, then you color all the people with left. Or you can color right, I don't care. Same thing with attached or unattached earlobes. You can pick which thing is going to be the trait you are studying. So coloring it in does not mean dominant or recessive. It just means this person has the characteristic that we are studying. Now, does anyone have any questions about the symbols that they want to ask while we're here? All right, so we're going to do just a few examples that show in an actual pedigree, an actual family tree, what is going on. The first thing that I'll comment on is this. A pedigree is what we call the picture of the family tree. So when you see the word pedigree, that's what we're talking about. Now, sometimes a genetic characteristic might be autosomal dominant. So we have to remind ourselves what an autosome is. Anything between chromosome 1 and chromosome 22 is an autosome. You might remember that it is anything but the X or Y chromosome, which are the sex chromosomes. So one of the things that we might ask you is we might show you a pedigree like this one and ask you, what type of inheritance do you see? For something to be autosomal, it means it's not linked to the X or to the Y chromosome. So the thing that you would look for is that males and females appear to be equally affected by it. So if something is autosomal, you should see men and you should see women that are affected. There shouldn't be a really disproportionate number of either. It doesn't mean they have to be exactly equal, because these are people, and these are just probabilities, but it should be close. The other thing is dominant. For something to be dominant, you have to see it in each generation. If something doesn't show up in each generation, it is very unlikely that it is a dominant characteristic, because if something is dominant, you will show that trait if you have even one copy of the allele. So there should be no skipping generations. There shouldn't be a scenario where a grandparent has it, neither parent has it, and then one of the kids has it. That would be against the rules of dominance. So the example that I'd like to show you of autosomal dominance first is polydactyly. Poly means many. Dactyl means the digits that you have. So polydactyly means having more than 5 fingers. Now 6 would be the most common thing, but more is possible. So there's an X-ray of a person's hand who obviously has 5 fingers and a thumb, so they have 6 digits on their hand. Now, in the family tree, we've got 3 generations here to figure out. Since we said it was autosomal dominant, here is what I know right away. Anybody who has it has at least 1 copy of the dominant gene. Anybody who doesn't have it has to have 2 copies of the recessive allele. That's how dominance and recessivity work. Yes. Yeah. 6 functional fingers. Yep. Yep. Now, one of the questions that I'm asking at the bottom is what are the genotypes? Because that is typically something that we would ask you on a test. Here's a pedigree, here's who has it and who doesn't. Can you figure out the genotypes of some or all of the people in this family tree? So I would start by filling in things that I know for sure. So I know for sure anybody who doesn't have it has 2 copies of the recessive allele. Anybody who does has at least 1 of the dominant allele. I'm not sure what the other one is yet. So I would start by filling in all of the things that I know for sure. So now that I've filled those in, you'll see that if the person has the recessive characteristic, it's kind of easy to figure them out. There's only one way they can have it. But when the characteristic is dominant, we're often wondering, what is the other allele? And so you have to use the offspring to figure out what the parents must have had. Does anyone want to tell me what the grandfather up here, what is the other allele that he has? Is it the dominant or is it the recessive? It's the recessive. And how did you know it was the recessive? They have a son who has homozygous recessive, and the only way that could have happened is if both parents had that allele. So that is the logic we would use to fill in that second P. Now, how about person 2-2? So we would call this person 2-2, generation 2, number 2. What is their genotype? They definitely have 1 of the dominant allele. What's the other one? Okay, go for it. It has to be recessive. Why? Because that is all the mother had. She could only possibly have passed on a recessive allele. So since that daughter obviously got the dominant allele from the father, the mother must have passed a recessive allele. Now over here, for person 3-1, we would deduce that they have heterozygous as well, because their mother had recessive genes. Now, does anyone want to ask any questions about this example? So I have another one to show you. This one is Huntington's disease. Does anybody know anything about Huntington's disease? It's a bad one, honestly. It affects your nervous system. It reduces your ability to control your movements. So it's a neuromuscular scenario. It's pretty bad. Usually it is early onset. So you might have heard of Parkinson's disease. Huntington's is in the same sort of umbrella of scenarios where it's your nervous system communicating with your muscles that is not functioning properly. But it is not one that people generally survive. And it is autosomal dominant. Now, if I hadn't told you that this was autosomal dominant, here's how you would know that it was. I would say that this is autosomal because if I look, I see 1, 2, 3 men who have it, and 1, 2, 3, 4. 4 women who have it. That is pretty close to even. So there are males and females who seem to be equally affected. So I can say to myself, yeah, that's got to be autosomal. Now, how do I know that it's dominant? There are a couple of things that you want to check for. First, is it in each generation? If it is, it's probably dominant. The second thing that you want to check for is look for two unaffected parents. So for example, person 2,3 and 2,4. Neither of them is affected by Huntington's. For this to be autosomal dominant, it would be impossible for their offspring to be affected. So when I look and see that their offspring are unaffected, it follows the rules. So for something to be dominant, if I have two unaffected parents, then all of their offspring should be unaffected. If that's not the case, then I can't say that it's dominant. But usually the thing you're looking for is it in each generation? If you can see it in each generation, it's very probably dominant. Now, let's talk about the affected individuals. For example, let's talk about the grandfather, person 1,1. How do we know if he is homozygous or heterozygous? I know he has at least one dominant allele for Huntington's. How do I know what his second allele is? It's the same reason we knew on the last one. Yes. For example, because of daughter number 6, he has to have a recessive allele because she does not have Huntington's. Her genotype is little h, little h. The only way that could have happened is if the father also had one of the recessive alleles to pass on. So when you're trying to figure out genotypes, look for people who are homozygous recessive. They are your key to figuring out what other people's genotypes are. Now, does anyone want to ask any questions about this example with Huntington's? Logan? No? Stretch? Anybody? Okay, so that's autosomal dominant. The other side of this coin would be autosomal recessive. Autosomal means the same thing. Men and women should be pretty close to equal, or we shouldn't see an obvious sway towards one gender. Recessive is a little bit trickier to identify. When things are recessive, they don't show up frequently. So when you're trying to decide if something is dominant or recessive, recessive characteristics, you should see few affected individuals. There shouldn't be a lot of people who are affected by it. Now, specifically, a thing that you can look for is this. If two unaffected parents have affected offspring, so that's the opposite of the last scenario. In the last scenario, if two unaffected parents mated, they had to have all unaffected offspring for it to make sense. But here, two unaffected parents could have affected offspring. And that would be a clue that we would use to say for sure, yeah, this needs to be a recessive characteristic. So there's two examples of human conditions that show this type of transmission. Probably the first one you haven't heard of, but I'm mentioning it because, one, I've seen it in diploma questions before, PKU, and two, it has to do with amino acids. It is when phenylalanine conversion to tyrosine is limited. And I'm mentioning this because I could see how a person who was writing questions would say, hey, here's an opportunity for me to ask a question about DNA transcription translation and then ask a genetics question with the same context, which they love to do. Do I think you need to memorize this? No. I'm just letting you know so that if you happen to see PKU show up, you're like, oh, okay, I heard about that. It's autosomal recessive. So, yeah. So because phenylalanine and tyrosine are amino acids, and to get an amino acid, I have to do translation of my mRNA into amino acids. I could see that would be the link. So we could ask a question about that with some sort of code, and then a question about this, yeah. Now the other one is cystic fibrosis. Does anybody know about cystic fibrosis? So cystic fibrosis usually has to do with respiration. In cystic fibrosis, I've often heard it being described as you're drowning from the inside. Basically, your lungs are full of mucus and fluid to a point where sometimes it becomes impossible to breathe. And so when a person drowns, water would probably enter their lungs, but a person who has cystic fibrosis would feel like that all of the time. So cystic fibrosis is basically fluid in your lungs, limiting your capacity to breathe. Now I have two little sample pedigrees here to show two different things. On the pedigree on the left, we're using this extra representation that I'd like to remind you about. If the circle or square is half colored, it means that this person is a carrier of a recessive allele. So we don't always use that symbol. We only use it if we're talking about something that's recessive and the person is carrying it but doesn't actually have the condition. So in this particular family tree, these two individuals are affected. Their parents are carriers, which means they don't actually have the disease, but they have the allele that causes the disease. So their parents would not have cystic fibrosis, if that's what we were studying, but both parents have one copy of the recessive allele that causes it. So sometimes you might see these half-colored in symbols, and that is what it means. Now, on your family trees that you're going to do, only color things in halfway if you're sure that it's a recessive characteristic. If you're not sure, ask me and I'll help you. And if you're doing something that's dominant, you won't be half coloring in any of the circles or squares. Now over here is an example where we haven't colored in the squares halfway. And I would say that this is pretty typical. The reason it's typical is because we like to ask, as teachers, do you know who would be a carrier for this disease without me just telling you? So if this individual down here has cystic fibrosis, but their parents do not, I could figure out that their parents were both carriers. So it is very typical of a diploma question to ask you, hey, if you know who's affected, who are the people that are heterozygous? Heterozygous people are carriers. So for example, both of that person's parents would have to be carriers. I also chose this one because it illustrated cosanguineous relation. That means people who were already related to each other. Does anyone want to ask any questions about recessive characteristics or being heterozygous? So then we have one last type of inheritance to go over and what it would look like on a family tree or on a pedigree, and that's X-linked or sex-linked characteristics. Sex-linked inheritance would look different depending on which chromosome is affected. If it's the X chromosome, females can be carriers and they have less chance of being affected. Males cannot be carriers and they have a greater chance of being affected. So like we saw with all of our practice Punnett squares, if it's on the X chromosome, it is more likely that a male will have that trait. It doesn't mean that a female won't. It just means that she has less of a chance. And very specifically, females can be carriers. So I'm just going to remind you in terms of genotype what that means. A carrier is someone who is heterozygous. That means they have one copy of the regular allele and one copy of the allele for whatever condition we're studying. Now, if it were on the Y chromosome, only men would be affected, only males. And we would say it would be passed from father to sons. And it would be passed from a father to all of his sons because the father has to pass his Y chromosome on to sons. So one of the textbook questions, nobody asked about it, but maybe you'll take a look at it and someone will want to ask, was about deafness in dogs, and it was on the Y chromosome. And that question illustrated that only males were going to have that condition because it was on the Y chromosome. Now, since something on the Y chromosome only affects males, you would only see squares colored in on the pedigree. I would think that this would be a fairly rare scenario to ask about. It is much less probable than it being X-linked. Now, these are some examples of things in humans that are X-linked and that are ones that I've seen questions about before. Obviously, color blindness and hemophilia, because we've seen them before. Muscular dystrophy is another one. There's a few different types of it. Muscular dystrophy is the progressive wasting of your muscle tissues to a point where you can no longer control your muscles. So I have a little sample picture here showing a little family tree. And I just want to highlight how I know that this is an X-linked characteristic. First of all, I'm going to count and see that there are, in total, 7 males and 1 female who are affected. That is disproportionate. That is a big enough difference for me to say, that's way more men than women. This is probably X-linked. Now, my other question is it dominant or is it recessive? And we're going to say it's recessive. And the evidence that I would use to prove that it was recessive would be, for example, these 2 parents and this child. Those 2 parents were unaffected, but they had a child who was affected. If it were dominant, that would be impossible. But since it's recessive, we have 2 unaffected parents with an affected child. And so if I asked you what mode of inheritance is represented, and you were writing it down, this is what you would say to me. X-linked because there's more men. Recessive because, for example, the 2 grandparents had a son who was affected. Now, the last thing I want to show you is an example of a real, actual scenario with real, actual people. It's about hemophilia in the royal families, and this is like their actual family tree. I would highly not recommend that you try to copy it down because that's not the point of it. I just wanted to give you a frame of reference with some actual people. Now, before I do that, does anybody have any questions that they want to ask about any sort of symbol or thing that you see on a pedigree?
Why is that one
like over here. So that's my one female who's affected. So what we're saying is, it's not that females are never affected by something on the X chromosome, it's just way less likely for them to be affected. So that's an affected female. All of these little diamonds down here, someone asked me this morning, those are babies that are not yet born, so we don't know what the sex of the baby is yet. We just know that there will be offspring there. Does anyone else have questions that they want to ask about pedigrees? So I'm just going to show you this so that you can see. It's a really big tree because this is of actual people. So if you take a look up here, there's Edward and Victoria and then Albert and Victoria. So that's the beginning of this. And then there are a lot of branches, so I'm just going to identify some people. Right here, that's the Russian family that we saw a question about before. So that's the Tsar and his wife, their daughters, and the son that was a hemophiliac. So they were part of one of the contexts on the last test that you guys did. And in that question, it talked about mitochondrial DNA being the same for the people in this family and Prince Philip over here. So Prince Philip is the one who was married to Queen Elizabeth. For example, Prince Charles is their son, and then William and Harry would be his sons down there. But if you follow this line up, there's Prince Philip. They have, oh, there's my finger. They have the same grandmother up there. And so that is why their mitochondrial DNA was the same. But if you look, this is the English royal family, the Russian royal family. There's the Spanish royal family over there. They all have similar ancestors. So they're all coming from the same piece of family tree. This is where you see sometimes the effects of consanguineous relationships where, because people have the same ancestors, they carry the same DNA, so sometimes their symbols would be drawn with two lines.